Nickel is a 3D transition metal with an atomic number of 28. Nickel was used for centuries before its technical discovery, but it was isolated by a Swedish scientist from a red-colored ore German miners believed contained copper. Nickel is a ductile, malleable metal that is very strong and corrosive resistant. It is completely unreactive in its metal form and insoluble in water. However, it can be soluble in dilute acids, but the only common oxidation number is +2. Nickel is the seventh most abundant transition metal, with Canada being the leading nickel provider. At its discovery, nickel was thought to be useless, but now alloys containing nickel, particularly stainless steel, are valuable materials in today's world. Nickel is ideal for alloy formation due to its strength, hardness, and corrosion resistance. Nickel is also used for electroplating, rechargeable batteries, and guitar strings. In 1899, Ludwig Mond developed a process for extracting and purifying nickel, a process now called the Mond process. This involves the conversion of nickel oxides to pure nickel metal. The oxide is obtained from nickel ores by treatments including concentration, roasting, and smelting of the minerals. In the first step of this reaction, the nickel metal reacts at 60 degrees Celsius with carbon monoxide gas to form tetracarbonyl nickel, a colorless yet toxic gas. In the second step, heating this gas to 200 degrees Celsius shifts the equilibrium in the opposite direction, resulting in 99.95% pure nickel. The extraction of nickel from metal ore can also take place through an electrolytic process, in which the impure nickel is cast into the anodes, and solutions of nickel sulfate and chloride are used as electrolytes. This results in the deposit of 99.9% pure nickel at the cathode. Generally, nickel complexes have octahedral geometry. Hexaaqua nickel 2 ion is a pale green color, but the addition of ammonia yields the blue hexaamine nickel 2 ion. While octahedral complexes are preferred, tetrahedral compounds in the form of halides do exist, such as the tetrachloronickelate 2 ion, formed by adding hydrochloric acid to hexaaqua nickel 2 ion. This yields a blue complex. A few square planar compounds do exist, such as the yellow tetracyano 2 ion, but octahedral complexes are much more common.
Palladium, abbreviated Pd, is a metal categorized in Group 10 of the periodic table with an atomic number of 46. It is a steel white metal that does not tarnish in air. Palladium is the least dense and lowest melting of the platinum group metals, which consist of ruthenium, rhodium, palladium, osmium, iridium, and platinum. When allowed to cool after heating, palladium is soft and ductile. Cold working increases its strength and hardness. At room temperature, palladium is able to absorb up to 900 times its own volume of hydrogen. Hydrogen readily diffuses through heated palladium, purifying the gas. Palladium was discovered by William Hyde Wollaston in 1803 in England while analyzing samples of platinum ore obtained from South America. Although it is a rare element, palladium tends to occur along deposits of platinum, nickel, copper, silver, and gold. It was named after the asteroid Pallas, which was discovered around the same time of palladium. There are 6 stable isotopes of palladium, with palladium 106 being the most abundant. Palladium 104 is used to produce radioactive palladium 103, which is used to fight prostate cancer. Palladium 108 can also be used to produce radioactive palladium 109, which is used in cancer therapy as well. Can be used in various ways. Palladium is growing in popularity in jewelry making because it is a strong and durable metal, yet has a low density, making it easier to wear than other metals. It's also used for springs in watches. Palladium can be used in the production of surgical instruments and electrical contacts for the same reasoning. It is also becoming popular in dental fillings and crowns due to its lower cost than gold or platinum. It's most widely known as a catalyst for hydrogenation and dehydrogenation reactions. Palladium can also absorb hydrogen gas, purifying it in the end. Palladium-containing components are used in virtually every type of electronic device. Although each component has a fraction of a gram of palladium, the volume produced results in significant consumption of palladium. It can also be used in coinage, photography, cancer treatment, and in catalytic converters that reduce the amount of toxic byproducts in the exhaust of automobiles. The production of palladium is a very complex industrial process because palladium is found in ores mixed with other metals. Once the ore is extracted, it undergoes preliminary treatment with a mixture of hydrochloric acid and nitric acid. This gives a solution containing complexes of gold and platinum, as well as H2PdCl4. The gold is removed from this solution as a treatment with iron chloride. The platinum is precipitated out by treatment with NH4Cl, leaving H2PdCl4. The palladium is precipitated out by treatment with ammonium hydroxide, leaving the palladium complex. This yields palladium metal by burning.
Platinum is one of the rarest metals in Earth's crust. It is most commonly found as a placer deposit, meaning that small grains of platinum are scattered among larger grains of other materials. It is also found alloyed with other metals, most commonly nickel and copper. Here are some properties of platinum. Platinum has a relatively high melting point at 1,768 degrees Celsius. It's non-oxidative even at high temperatures, meaning that no oxide coating is going to form on the surface of platinum no matter its temperature. Platinum is extremely ductile, meaning it can be bent and twisted and elongated very easily. Platinum is also very non-reactive. The non-reactivity and non-oxidative properties of platinum are why some people refer to it as a noble metal. Platinum 2 chloride and platinum 4 chloride, as we can see, form very interesting structures. The first step in the production of platinum involves taking platinum ore, or a platinum-containing alloy, and oxidizing it with aqua regia. Aqua regia is a mixture of nitric acid and hydrochloric acid. By itself, platinum will not react with nitric acid, and platinum will not react with hydrochloric acid. However, once nitric acid and hydrochloric acid are mixed together, platinum will react with them. This reaction is relatively slow, and a side reaction will occur between nitric acid and hydrochloric acid, meaning that you need to constantly be adding nitric acid and hydrochloric acid to the system, depending on how much platinum you're trying to dissolve in them. The compound that's produced is called chloroplatinic acid, and this can be isolated by heating the resulting solution and allowing the compounds to evaporate off of it. The second step in the production of platinum involves the formation of ammonium hexachloroplatinate. We take the chloroplatinic acid, we dilute it in water, and react it with ammonium chloride. This forms the ammonium hexachloroplatinate. This compound is extremely insoluble in the presence of ammonium chloride, so if we add excess ammonium chloride to the system, we will get this solid to form out of it. This reaction is easily reversible by treating the product with chlorine gas. The final step in the production of platinum involves reducing platinum from the ammonium hexachloroplatinate. We do this by treating the ammonium hexachloroplatinate with hydrogen gas at 200 degrees Celsius. The form of platinum that's produced is referred to as platinum sponge. This is a form of platinum that's over 99.9% pure, and it can be seen on the right as a black, sandy-looking mass.